Every lunar lander for 60 years has used legs, until SpaceX proposed landing Starship directly on its belly. Their 2021 Artemis design would use a 9-meter steel hull with crushable aluminum mesh, eliminating 8 to 10 tons of hardware. Could this radical concept actually work? NASA's safety board discovered a critical flaw. The legless design had zero redundancy. One engine failure during descent meant catastrophic crash. Even worse, simulations showed the Raptor engines would carve craters 1 to 2 meters deep, undermining the landing pad Starship just created. What made NASA force SpaceX back to traditional legs? Let's dive right in. When SpaceX won NASA's Human Landing System contract in April 2021, their proposal included engineering decisions that made veteran aerospace engineers do a double-take. The design showed a massive spacecraft touching down on a titanium ring just 8 millimeters thick, with no traditional landing gear extending from its base. How did they plan to pull this off? The answer lay in Elon Musk's core philosophy. If a part doesn't exist, it can't fail. Landing legs aren't simple metal struts. They're miniature systems packed with folding mechanisms, hydraulic pistons, sensors, actuators, and control software. Each leg creates thousands of potential failure points. By eliminating them entirely, SpaceX could remove 8 to 10 tons of hardware, including hinges, titanium struts, and dampening systems. That's 7 extra tons of payload capacity, enough supplies to extend astronaut stays by several days. But removing legs created an obvious problem. How do you prevent a 50-meter-tall spacecraft from sinking into lunar dust or tipping over on uneven terrain? SpaceX's solution was called Plume Surface Interaction, or PSI. About 30 seconds before touchdown, a ring of nozzles would blast hot gas at 45-degree angles, blowing away loose regolith and compacting the ground below. The process would create a temporary landing pad 20 to 30 centimeters thick, capable of withstanding 25 kilopascals of pressure, roughly equivalent to a car tire on Earth. Computer simulations showed this compacted surface could even flatten slopes up to 10 degrees. The landing sequence itself was precisely choreographed. During the final 10 seconds, 6 Raptor engines would throttle down to just 5 to 8% power, slowing Starship to less than 1 meter per second. A crushable skirt made of 3D-printed aluminum mesh would deform on contact, absorbing up to 70% of impact force. The reinforced steel hull would do the rest. On paper, it was elegant engineering at its finest. Then engineers explored an even more radical variant, horizontal landing. In this version, Starship would descend vertically as normal, then tilt forward to about 30 degrees just before touchdown. It would belly land using a thick composite pad, with 4 autonomous anchors firing into lunar soil to hold it in place. Why consider such a dramatic departure from vertical landing? The benefits were surprisingly practical. A horizontal position lowered the center of gravity dramatically, spreading 150 tons across 160 square meters, reducing ground pressure by more than tenfold compared to legged designs. Astronauts could exit via a 3-meter staircase instead of a 30-meter elevator. Rovers could roll directly out through side doors. The hull's interior offered over 100 cubic meters of space, larger than the entire ISS pressurized volume. Crew could even pile lunar regolith on top for natural radiation shielding. A horizontal Starship wasn't just a lander, it could become an instant lunar base. But reality hit hard. Starship's structure was optimized for vertical loads, not horizontal orientation. Turning it sideways introduced massive bending stresses along its 50-meter steel frame, forces the vehicle was never designed to handle. Fuel tanks posed another challenge. In 1/6 Earth gravity, liquid methane and oxygen would slosh unpredictably, creating pressure imbalances that could destabilize the spacecraft during critical moments. The biggest obstacle was simple physics. Once horizontal, how would Starship stand up again for the return journey? A human-rated spacecraft must not only land safely, it must launch home. Lifting 150 tons upright on the moon would require elaborate systems that negated every weight advantage the horizontal concept offered. By late 2022, NASA's Aerospace Safety Advisory Panel delivered their assessment. The conclusion was firm: too risky for crewed missions. The problem wasn't theoretical, it was the moon's surface itself. Lunar regolith varies wildly in density. Some areas are rock hard, others can swallow a probe's leg a meter deep. Traditional landing legs spread weight across multiple, widely spaced points. If one leg sinks into soft regolith, others compensate to keep the vehicle upright. Without legs, if one side of Starship's hull sank just 1 meter, the 50-meter vehicle would tilt 25 degrees and topple in seconds. There would be no recovery. The crew and mission would be lost. Landing legs with shock absorbers and terrain compensation systems can extend or compress individually, adapting to slopes and keeping the lander stable, like a table with adjustable legs on uneven ground. The legless design had no such forgiveness. The engine exhaust created another critical problem. Even throttled down, Starship's 6 Raptors produce exhaust velocities exceeding 2,000 meters per second, enough to carve a crater 1 to 2 meters deep during descent. Simulations showed this effect would undermine the compacted landing pad that the spacecraft had just created with its gas jets. The vehicle would essentially dig its own grave. Then there was lunar dust. Regolith particles are electrostatically charged, razor-sharp, and clingy. Once disturbed, they don't settle. They float. Clouds of it could coat sensors, damage seals, and infiltrate life support systems. For astronauts working nearby, the dust posed serious respiratory and eye hazards. NASA's requirements were clear. A human lander must minimize plume effects, not intensify them. The final nail came from safety certification requirements. NASA mandates at least 2 levels of fault tolerance for any crewed spacecraft. In the legless design, a single engine failure during final descent could unbalance thrust and cause catastrophic crash. There was no redundancy, no backup structure to absorb a misfire or compensate for a tilt. No matter how much weight it saved, the design couldn't meet human rating standards. By early 2023, SpaceX quietly shifted to what they called Option B, a redesigned Starship HLS with 6 retractable titanium landing legs. These new legs feature self-adjusting pistons and honeycomb dampers, capable of compensating for terrain slopes up to 15 degrees. They add complexity and weight, but also stability and redundancy. The trade-off became the defining choice: elegant simplicity versus proven reliability. The leg version may look less revolutionary, but it represents something more valuable: experience meeting innovation. It's a design that acknowledges the brutal truth. The moon doesn't forgive boldness. Physics always has the final word. Yet this story isn't finished. SpaceX's legless concept was one of the most daring engineering proposals of our time, a vision where simplicity defeats tradition. But it taught us something crucial. Even the most elegant ideas must survive the test of reality. The moon demands more than innovation. It demands proof. The updated legged Starship may look conventional, but it represents the wisdom of experience. It's a compromise between breakthrough thinking and survival. In space exploration, proven stability must outweigh theoretical perfection. That's not defeat, that's evolution. Here's what makes this fascinating. As we look beyond Artemis toward permanent lunar bases and Mars colonies, the legless and horizontal concepts might return. When we no longer need to launch back home, when we start building on the moon instead of just visiting, these radical ideas could find their moment. Because in spaceflight history, no concept ever truly dies. It simply waits for the right conditions to land. Elon Musk's frustration with landing legs comes down to one thing: they add weight, complexity, and failure points. His solution on Earth? Mechazilla, a massive tower with robotic arms that catch boosters midair. But could we ever build something like that on the moon or Mars? Could future starships use side-mounted engines for horizontal landings, leveraging those massive flap hinge points that already handle 400 tons of force during atmospheric entry? The engineering challenges are real. Side-mounted engines create uneven structural stress. Fuel slosh in horizontal tanks becomes unpredictable. But these problems aren't impossible. They're just waiting for the right mission profile. What's your take? Should SpaceX pursue legless landing for cargo missions? Could horizontal Starship work as a permanent lunar base? Drop your thoughts in the comments below. I read everyone. If this deep dive into SpaceX's engineering decisions got you thinking, hit that like button and subscribe to Space Update 24 Hours. We're building a community of space enthusiasts who want the real story behind the headlines. Ring that notification bell so you never miss our next breakdown. Thanks for watching, and I'll see you in the next one.